In part 2 of Strange New Worlds, the Properties of Exoplanets, we now turn to the question that we really all like to have the answer to. We found Jupiters and Neptunes. What about Earths? Current methods of exoplanet detection are only now becoming sensitive to the detection of Earth-sized planets. Radio velocity methods must become about 10 times more precise in order to detect the orbital motions of Earths reflected in the wobble of their parent stars. This requires getting down to measuring speeds of 10 centimeters per second, an extremely slow walk, in fact, a slow crawl, which is very, very challenging, but appears to be within realm of next-generation spectroscopic instruments currently being built. The transit method is probably more promising because we can get the precision of measuring the dimming of a star as the planet transits in front of the face of the star, but we have to get down to where we can measure changes in brightness of less than 1 part in 10,000. That is doable with current technology, and in fact was within the capabilities of the instruments on board the Kepler spacecraft, and is well within the capabilities of next-generation space-based transit studies that are being prepared for launch in the late 2010s and early 2020s. Indeed, the Kepler spacecraft using transits has recently found the first good Earth-sized candidates. Now, let me be careful here. We're referring to Earth radius, not Earth mass. The transit method cannot tell you the mass of a planet unless you have some way to measure its orbit. In order to measure the orbit gives you the mass through Newton's version of Kepler's third law. What the transit tells you is the radius of the planet, and so we're making the leap of inference that if an object has the radius of the Earth, and we assume that it has the composition of the Earth, then it therefore should have something like the mass of the Earth. There are alternative techniques, like gravitational microlensing, that are very promising. These will, in fact, return a mass and could give us the first really firm detections of Earth mass or even Mars mass planets around other stars. But these techniques, while they've been making excellent progress, and indeed work by myself and my colleagues here at Ohio State, has been trying to push the state-of-the-art of gravitational microlensing techniques, we're still a few years away from delivering. A brand new project being started by some South Korean astronomers may change this in the next few years, so stay tuned. But anyway, getting back to our story. If we look at the distribution of planetary masses that are known through various techniques, transits, radio velocities, microlensing, and we look at the distribution of them, we see this funny double-humped profile. These range up in size, getting upwards of 20 times the mass of Jupiter, down to Earth mass objects down here. And there's really only onesies and twosies of planets that have confirmable, or at least inferable, masses of order the mass of the Earth. There's a big hump of Neptune mass objects, fewer Saturn mass, and a whole bunch of Jupiter mass objects. So the frontiers, the place we are pushing the state of the art, is to find these, the elusive Earths. This gives you an idea of some of the Earth-sized planets that we've been able to find with the Kepler spacecraft. This is the Kepler-20 system. It consists of 5 planets, 2 with near-Earth-sized planets around a Sun-like G-type star. But all of these are hot planets. They are all so close to their parent star that they're probably completely uninhabitable. They're closer to their parent stars than Mercury is to our Sun. Even when you scale for these slight differences in temperature of the star, it doesn't help you any. These are the systems of Kepler-20. Kepler-20e and Kepler-20f are approximately the size, a little bit smaller than the Earth and a little bit larger than the Earth. The artist here, in the NASA habit, seems to want to draw Earth-like planets having plausible atmospheres and continents, making it look even more Earth-like. But again, remember that the colorations that are shown here are purely speculative. The Kepler-42 system has 3 planets close in size between Earth and Mars size around a red dwarf star. So here are the 3 Kepler-42 planets, Kepler-42b, C, and D, one of which is getting down to the size of Mars, shown here for scale. Like the Kepler-20 system close in rocky planets, these 2 are all hot planets. These are too close to their parent stars to be possibly sustaining an atmosphere or any form of liquid water. This brings us to the idea of what it is we're looking for when we're looking for another Earth. Clearly, we're finding things that are plausibly the size and mass of the Earth, even things that are becoming plausibly the size and mass of Mars. But what we don't want to find is things that are simply Earth size. We want to find things that are Earth-like, which means they have atmospheres and liquid water, and in fact are habitable. And this brings us to now a consideration of what we refer to as the habitable zone. Astronomers call the habitable zone the region around a star where liquid water would be stable on a planet's surface. Some people, and I count myself among them, extend this definition further than the traditional definition I show here and say where liquid water would be stable on a planet's surface for geological time. We know that evolution and the development of life requires long periods of time, millions and billions of years. It doesn't do any good if you only have liquid water on the surface of a planet for, say, a few centuries after a heavy comet strike, and then it all evaporates. You want that liquid water to be stable over geological timescales, giving the processes of life, including evolution through natural selection, time to operate. The other thing that's buried underneath our definition of habitability is a certain provinciality of outlook. It refers to stability of liquid water on the planet's surface, and it assumes that one has stable liquid water on a planet with an Earth-like mass and an Earth-like atmosphere and composition. Some of those, or none of those, may in fact be the case. Nonetheless, it's a starting point. Where is this habitable zone? Well, it has an inner edge and an outer edge. A conservative estimate would place the inner edge of our habitable zone at about 0.95 astronomical units and the outer edge at about 1.4 AU, shown by the bright green band in this diagram to the right. An optimistic stretch of the habitable zone definition, one that's actually probably much better, moves the inner edge of the habitable zone down to 0.84 astronomical units, well inside the orbit of the Earth, but not all the way to the orbit of Venus, and lets it stretch all the way out to the orbit of Mars, and a little bit beyond, placing Mars just skirting the outer edge of the optimistic habitable zone. How are these inner and outer boundaries determined? Well, the inner boundary is determined by the point at which it becomes so hot that all liquid water on the surface of the planet will evaporate, end up as water vapor in the atmosphere, and trigger a runaway greenhouse effect, causing the atmosphere to heat up and dramatically dry out, as all the water vapor is broken up by sunlight into hydrogen and oxygen and lost into space. This is what happened to the planet Venus. Venus is too close to the sun to be able to hold liquid water, and while it may have started with an atmosphere whose composition, including water content, was very much like that of the Earth, in the first billion years of the solar system's existence, Venus experienced a runaway greenhouse effect. All of the water was evaporated away and the planet dried out, leaving behind a hot, heavy carbon dioxide atmosphere. Indeed, the surface of Venus is an unhospitable 700 degrees everywhere on the surface, and its surface is entirely hidden from the outside by thick clouds of sulfur dioxide and sulfuric acid. There's very little water on Venus because it's all escaped away into space. The outer edge of the habitable zone is set by the point beyond which it is too cold for liquid water to exist on the surface, and the water freezes into ice. Water freezing into ice is believed not to be very good for the formation of life, because life as we understand it, carbon chemistry, requires a liquid medium, liquid water, for that chemistry to occur. We see in the outer edges of the habitable zone of our solar system the planet Mars. Mars is tiny, has a very much lower gravity, and was unable to hold on to a lot of its atmosphere. As a consequence, while there's a lot of water on Mars, and indeed the composition of Mars's atmosphere probably started out the same as the composition of the atmospheres of the Earth and Venus, including the water content. But Mars is small and Mars is cold, and once its geology shut down and its atmosphere began to thin out, it became too cold to sustain liquid water at the surface, and all the liquid water that may have been there froze out below the ground. Mars experienced a big freeze-out, which led to all of its liquid water leaving the surface, leaving behind a dry, cold desert world. However, there may be significant amounts of water below the surface, perhaps in ice form, and this is a major point of exploration for current and future Mars missions. Furthermore, Mars was not always like this. Just like Venus was very different in the first billion years of the solar system's life, so too we think that Mars may have been very different up to a billion or so years ago. Indeed, many astronomers are now beginning to believe that the evidence of the Mars rovers is showing us, very clearly, that at one time in the past of Mars there was lots of standing liquid water on the surface. We see clays, we see hydrated minerals, whose explanations can only be that they formed in the presence of water stable on the surface for a geologically long time. While Mars is a cold, dry desert today, in the distant past, it may have been very different. This is what we mean by habitability. And often when people look at the positions of planets within those exoplanetary systems, what they would like to find is an Earth-like planet in the habitable zone of its parent star. Such planets are the most likely places to be looking for surface life elsewhere in the universe. However, this definition of habitable zone is a little shaky in the sense that it really has a lot of underlying assumptions. And sometimes those assumptions are in need of questioning. We're going to look at what some of those assumptions are a little bit later in the class. But for now, we're going to talk about what the habitable zone is and what it means for some of the exoplanets we've discovered, and a caution when looking at news items about it. As we introduced during part 1 of this lecture, the best exo-Earth candidate to date is Kepler-186f, a Earth-ish planet, I should say, not really Earth-like, but Earth-ish, about 1.1 times the radius of the Earth, orbiting around an M-dwarf star about 500 light-years away from Earth. If you scale the brightness of the M-dwarf to the brightness of the Sun, then, as shown in this picture on the right, this green band is the estimated habitable zone for liquid water on the surface of an Earth-like planet around the host star of Kepler-186. The Kepler-186f planet is well inside the habitable zone for this red dwarf star. However, the surface of the planet may have a stronger gravity than the Earth, and we don't know if it has an atmosphere at all. So while the artist has taken considerable artistic license to endow Kepler-186f with continents and oceans of liquid water and an atmosphere with clouds, even a little bit of snow up on the top, beware. This is just an artist drawing a picture. All we really know for sure is that Kepler-186f is 1.1 times the radius of the Earth, and if we simply scale the habitable zone of our solar system to a star of the brightness of the M-dwarf Kepler-186, then yes, indeed, Kepler-186 lies in the habitable zone, but that is not the same as saying it is definitely habitable. Similarly, another planet that was once put forward in NASA press releases as the first habitable world discovered beyond our own solar system is Kepler-22b. Kepler-22b, unlike Kepler-186, is orbiting a Sun-like star, just like our Sun. It's a little bit fainter, and so its habitable zone extends a little bit further in than the habitable zone of our solar system, shown here in the bottom part of this diagram, which shows our Sun and the orbits of Mercury, Venus, Earth, and Mars. Kepler-22 appears to lie near the inner limit of the habitable zone of the Kepler-22 home star. This places it a little bit this is a little bit of an optimistic extension inward, but not too bad. However, Kepler-22b is a super-Earth. It's an enormous planet. Such a planet would probably have a strong enough gravity to hold on to a very heavy atmosphere. Very heavy atmospheres are prone to the formation of runaway greenhouse effects, causing their surfaces to heat up dramatically and boiling all the water away, eventually losing it to space, to the ultraviolet radiation from the parent star. By putting a super-Earth very close to the inner edge of the habitable zone, it's a pretty good chance that maybe, just maybe, this may not be a very habitable world at all. So whenever you hear an announcement that a planet has been found in the habitable zone of its star, take a deep breath and take it with a grain of salt. Habitable zone refers to Earth-mass planets with Earth-like composition and Earth-like atmospheres. If you have a planet that's much larger or much smaller, or perhaps even a different composition, it's not clear that the principle of habitability in our solar system necessarily applies to other solar systems. But beyond the question of whether we're finding habitable planets yet, we're certainly getting things that are in about the right location, and that's the exciting part, because it means the hunt is on. We've also found some very interesting planetary systems. For example, Kepler-16. Kepler-16 is about 1/3 the mass of the Jupiter, orbiting a binary star consisting of a K and an M star, two stars slightly smaller than the mass of the Sun, one of which is kind of yellowish and the other one is a red dwarf. This system, for those of you science fiction fans in the audience, resembles the Tatooine system of the original Star Wars films. The tight binary is in the inner part of the solar system, and this planet is actually orbiting in it far enough away from this inner binary that it's in a stable orbit over long periods of time. Indeed, circumbinary planets like this have been discovered in considerable abundance, especially by the Kepler project. It shows us that planets can form nearly anywhere that stars form. This was a great surprise. In fact, part of what it's telling us is that our initial estimates about how often we see planetary systems may in fact be in need of revision upward. The feeling now among many scientists, and I include myself among that number, is that the data seem to indicate that every star below a certain size forms a planet. Maybe even stars bigger, but nearly every star, like the Sun, or slightly less massive, or slightly more massive, may possess one or more planets. That greatly extends the possibility for planetary systems that could potentially harbor life throughout a galaxy with 200 billion stars. This is the present Kepler Hall of Fame as of January 2015, the last time they published it, showing plausible, maybe, kinda, sorta, small habitable zone planets discovered with Kepler. The numbers? Currently 7, of which maybe 1 or none will actually survive close scrutiny. We've already seen Kepler 186f, but there are a number of other of these, all of which are in the super-Earth category. We haven't yet, bottom line, found an Earth-like planet in an Earth-like orbit around a Sun-like star, or even robustly in the habitable zone of its star, even if the star is not Sun-like. However, the hunt is on. We're continuing to search for many planetary systems using many complementary methods, many of these methods becoming quite sophisticated, and is becoming a greater focus of both technological development and the effort of astronomers to understand the data. The ultimate goal we want is to find another Earth, but there are other goals as well. We would really like to find more solar systems that are like our own. Right now we're unusual, but as I've shown, hopefully, earlier, this is largely a selection effect because we're still in the early days of exoplanet exploration. How common are planets? The answer seems to be very common indeed. How common are systems like our solar system? We don't know the answer to that yet, but they may be more common than we think, at least given the initial data, so stay tuned. Of course, the ultimate goal, the one we'd really like to get to, is finding another Earth capable of harboring life. Wouldn't that be a marvelous discovery? To find a place within a few tens or hundreds of light years of the Earth that is plausibly have liquid water stable for geologic timescales on its surface. You can imagine that such worlds will be the subject of intensive inquiry to ask the question, is there liquid water? Is there an atmosphere? And maybe, is there life? These are questions we can't answer today, but they will be questions that may, I think, be answered in my lifetime and yours.